Matrix geometry. In this lesson, we look at several geometric aspects of linear operators. The standard basis is the set of unit vectors along the coordinate axis. We can use this matrix representation for the standard basis in three-dimensional space. Any vector can be uniquely written as a linear combination of the basis vectors. For example, the vector 2, 3, 6 equals 2 times e1 plus 3 times e2 plus 6 times e3. A usual geometric interpretation of a vector is an object with a prescribed length and direction in space. The length of a vector v in the standard basis equals the Euclidean norm, the square root of the dot product of v with itself. The length of the vector 2, 3, 6 is 7, which agrees with the Pythagorean theorem. A unit vector is found by normalizing a vector by its length. This identifies the vector with a point on the unit sphere, giving us its direction. The unit vector that corresponds to the vector 2, 3, 6 is 2 sevenths, 3 sevenths, 6 sevenths. The angle theta subtended by two vectors v and w can be found by using trigonometry. The cosine of theta is equal to the dot product of the unit vectors v hat and w hat, which is equivalent to the inner product of v and w, divided by the Euclidean norms of v and w. From this we have the identity, which says that the inner product of v and w equals the length of v times the length of the projection of w onto v. If the inner product of two vectors is 0, we say that the vectors are orthogonal. This can happen when either the vectors are perpendicular, or either vector has 0 length. Let's move on to matrices. There are 4 basic linear transformations. Matrices can stretch or shrink by changing the magnitude of vectors, possibly squashing the length to 0. Matrices can rotate, by changing the direction of vectors. Matrices can reflect, by changing the orientation of vectors. And matrices can shear, which is a combination of stretching, rotation, and reflection. Thinking of matrices in terms of geometric properties is helpful in developing a useful intuition. Let's look at the geometry of a two-dimensional linear transformations. Consider the 2 by 2 matrix ABCD. The matrix maps the unit vector in the x direction to the vector AC, which is the first column of the matrix. It maps the unit vector in the y direction to the vector BD, which is the second column of the matrix. Using this idea we can examine how a matrix maps an arbitrary object in the plane. Let's look at some specific examples. We'll use this sheet to demonstrate the effect of matrices on the standard basis. The identity matrix 1001 of course, has no effect and returns the original sheet. The diagonal matrix 2001 stretches the unit vector 10 along x-axis by 2, while maintaining the length of the 01 vector along the y-axis. Similarly, the diagonal matrix 1002 maintains the length of the 10 vector, while stretching the other unit vector. The diagonal matrix 2002 stretches both unit vectors equally. Note that 2 diagonal matrix equals the product of the 2 diagonal matrix and the 1 diagonal matrix, which equals the product of the 2 diagonal matrix and the 1 diagonal matrix. Stretching uniformly by 2 is equivalent to stretching first along the x-axis, and then along the y-axis, and vice versa. Consider the matrix 1101. The unit vector along the x-axis is unchanged but the unit vector along the y-axis is mapped to 1 at a 45-degree angle. This results in shear. The -1001 matrix multiplies the first basis vector by -1, which results in a reflection about the y-axis. The permutation matrix switches the roles of the two basis vectors. This results in a reflection about the line y equals x. The rotation matrix rotates both basis vectors by equal angles. The reflection matrix, the permutation matrix, and the rotation matrix are examples of orthogonal matrices, which preserve lengths and angles. Finally, this projection matrix squashes the sheet into a one-dimensional subspace, a line. The projection matrix is a singular matrix. It is impossible to undo this operation. Linear transformations in higher dimensions are analogous to transformations in 2 dimensions, just a little more difficult to visualize. A matrix always converts a sphere to an ellipsoid, and a cube to a parallelepiped. We will re-examine specifics such as change in volume, directional invariance, and the direction and amount of maximum stretch throughout the remainder of these lessons.